Hey everybody, welcome back to chemistry. And so with the last presentation, I was kind of pointing out the fact that a lot of times if you have a formula for a molecule and you're writing out a Lewis structure for it, you can write out more than one Lewis structure. And so there's sort of alternate forms of these Lewis structures. But what we also kind of noted is that a lot of times that neither one of those Lewis structures is really an accurate representation of the molecule. So what we do is we sort of merge those structures in our mind to produce something called a resonance hybrid, which is a better representation of the true structure of the molecule. Now, it can get a little bit worse than that, and the reason is this. And so with the last examples I showed you, basically you looked at the resonance forms of those molecules, and if you look at them carefully, you basically see that they're different in terms of where the bonds were between the different atoms, but they basically were equivalent structures. And with their equivalent structures, then they have similar energy. And so here what I'm going to talk about is the possibility that you're going to write out Lewis structures. You're going to have alternate Lewis structures, but the problem here is they are not said to be equivalent structures. In fact, there may be one structure that I kind of know for some reason that has a lower potential energy than other structures. And if that's the case, then the final resonance hybrid will be dominated by that particular structure that has the lowest potential energy. So the way I evaluate the potential energy of a Lewis structure is by calculating something called a formal charge for all the atoms in the structure. So let me talk a little bit about what formal charge is really quickly. So I'm going to write formal charge here. And formal charges are a bit of a pain, but it's something you have to go through again to evaluate which resonance form has the lowest energy. So the first thing to know about formal charge, it's not a real charge. So you're going to see formal charges on atoms. And so there we go. You're going to see formal charges on atoms, and you're going to see things like, well, we have an oxygen here that has a -1, or we have a carbon that's a +2, and things like that. You might think, oh, yeah, those are real charges, but they're not. So just keep in mind that they do not actually show that the atom has maybe a deficiency or excess of charge. Basically, a formal charge, what it really is, it just shows you how far the atom in its bound structure, bound to other atoms, how far the atom deviates from the normal valence of the atom. So let me give you a quick example of that. So let's say you have phosphorus. And so what you can do is figure out the normal valence of phosphorus. And so what you'll see, it's in group 15. So that would indicate that it has 5 valence electrons. And so how we sort of indicate that this has 5 valence electrons is by drawing 5 dots around it like that. Now, what you'll find, for example, maybe you'll have a phosphorus bound to, say, 2 atoms. And so it's bound to one atom like this, one to like this. It doesn't matter what the atoms are. I'm just kind of using X as an example. And then maybe phosphorus has retained its 2 electrons here, but maybe for some reason it picked up an extra electron here. So what we have to do in Lewis structures is evaluate how far its valence has deviated from the true valence of a phosphorus atom. And so the way you deal with that is you figure out the formal charge of this phosphorus, say, in this compound. And so if there is no formal charge for this phosphorus in this compound, in other words, the formal charge you calculate is 0, then it is not deviated from the 5 electron valence in the phosphorus atom. But if there is a positive charge, then it's deficient in, say, a valence electron. If it's a negative charge, it's in excess of 1 electron. So quickly, how would you do that? Well, in this structure, what you have to sort of remind yourself is in this shared pair of electrons between phosphorus and this X atom here, one of the electrons really belong to phosphorus, and one of the electrons belong to the atom X. And so here we can sort of see that because a shared pair is 2 electrons, one of them originally came from phosphorus. So we have another shared pair of electrons here, and here we have this electron here also, and this originally came from phosphorus. And so that's good. But look, now when I drew this structure, this phosphorus atom, I added in an extra electron. And so now it looks like phosphorus in this structure has deviated from its normal valence of 5. Now I can sort of account for 6 electrons around phosphorus. And so what I would have to do is to remind myself that this phosphorus really is sort of deviating from its normal valence. I have an extra electron, so here I'm going to put a -1 for the formal charge. Now, what you can do is you can sort of memorize a formula for figuring out formal charge. And so let me give you what that formula is. So formal charge is going to be equal to the valence electrons minus the lone pair electrons plus 1/2 shared pairs of electrons. So what I do when I do a formal charge calculation is for each atom I look up the total number of lone pairs of electrons and I add that to the shared pair of electrons which I've halved. Those two numbers are added and subtract that from the valence electrons and that should give me the formal charge. A simpler way to calculate formal charge is you can just often do it by looking at the structure, which is what we're going to be doing mostly in this class, is formal charge. If you have some kind of structure, the easiest way to calculate formal charge is just, again, take the valence electrons that the atom has minus dots, which are lone pairs in a Lewis structure, plus lines, which a line, if you think about it, is going to represent 2 electrons. One came from one atom, one came from another atom. And so here, a line would be 1/2 of a shared pair. So you can use this formula, it'll work perfectly well. Okay, so what I'm going to do now is I'm going to go ahead and draw a Lewis structure for a molecule. And what you're going to see is that there will be several Lewis structures that you can write. And so those Lewis structures you can call resonance forms. And then we're going to evaluate which of the resonance forms has the lowest potential energy. And we're going to be doing that by assigning formal charges to all the atoms in the Lewis structure. So the molecule we're going to be looking at is phosgene. So its formula is COCl2. It's phosgene. Okay, so first off, let us calculate a valence electron count. So carbon has 4 electrons, oxygen has 6 electrons, and then chlorine has 7 electrons, and there are 2 of them for a total of 14 electrons from chlorine. So it's 14 plus 10. So I'm seeing 24 electrons here, or 12 pairs. So let's quickly write out what this might look like. So here is carbon here in the center. It'll be in the center because it is the less electronegative of oxygen and chlorine. Oxygen on one end, chlorine's on the other end. Okay, so we have 12 pairs that we have to deal with. So pair 1, pair 2, pair 3, 4, 5, 6, 10, 11, 12. Okay, so what you can see, this is not a good Lewis structure because the carbon doesn't have an octet. So we're going to go ahead and produce good Lewis structures, but you can see that we can probably produce a number of different good Lewis structures that are basically correct, but only one of them, as I'll show you, will have a relatively low potential energy, and you have to figure out which one it is. Okay, so one Lewis structure we can make is by dropping this lone pair of electrons from the oxygen into the bond between carbon and oxygen. So let me write out this one down here. So we have carbon, and so we have double bond to oxygen here, and then we have chlorine here, and then we have a chlorine here. And so this is a perfectly good Lewis structure because you can see that all atoms have an octet. Now, another perfectly good Lewis structure we can write is, instead of dropping this pair from oxygen into the bond between carbon and oxygen, we drop this pair from chlorine into the bond between carbon and chlorine. So we'll do it for the left chlorine first. So let me write out that Lewis structure. It'll look like this. Okay, so that is a perfectly good Lewis structure. It is correct. All atoms have octets. And then I'll do the same thing, but this time what I'm going to do is move this lone pair from the right chlorine into the bond, so what we get is this. Okay, so it will look like this. Okay, so what I'm going to do is erase this structure here. Now, what you can probably see is we have written out 3 perfectly good Lewis structures because all the atoms in each of the Lewis structures have octets. And so these are resonance forms of this molecule. But here's the problem. One of these resonance forms has a lower potential energy than the other 2. And if so, it will make a bigger contribution to the final resonance hybrid structure. And so we have to figure out which of these forms, we have form A here, form B, form C, is the best at lowering the, or having the lowest potential energy. And so the way you evaluate that is by something called formal charge. And so what I have to do is go through and calculate the formal charges of each of these atoms in the Lewis structure. And so let's start out with this Lewis, or this resonance form A. So let's look at this carbon here. And so I'm just going to talk about how do we calculate the formal charge of carbon. So it is the valence, which is 4, minus dots plus lines. And so do we have any dots around carbon? No, we don't. So dots is 0. Do we have lines around carbon? Yes, we have 4. So there are 4 here. And so here what you can see is 4 minus 4 is 0. So the formal charge for this carbon here is 0. Okay, let's calculate the formal charge for this oxygen here. So this oxygen here is going to be, it has normally a valence of 6 dots. There are 4 dots around the oxygen atom. There are 2 lines plus 2. And so what you can see is formal charge is 0. Okay, let's calculate the formal charge of chlorine here. And so what this chlorine is going to be 7 is its valence minus, looks like we have 6 dots plus 1 line, so it's going to be formal charge of 0. And so this applies for both chlorines. So pretty much what we did in this calculation is what we see is that in resonance form A, that Lewis structure of A, the resonance form A, all the atoms we calculate a formal charge for, and it's 0 in every case. So that will be meaningful in just a second. Okay, so let's look at this a second Lewis structure and count formal charges for that. So if you look carefully, carbon here in the second Lewis structure B, it has, again, it'll have 4 valence electrons, and it's going to have 4 lines and no dots. And so what we can sort of quickly see is that this carbon here is basically the same as the carbon on the left. So this carbon on the left has a formal charge of 0. This carbon here in structure B also has a formal charge of 0. Okay, but here you can see the oxygen here in structure B has a different structure than in structure A. And so it's probably going to have a different formal charge. So we need to calculate this for this oxygen. So let's figure that out. So for this oxygen, the valence of oxygen is 6. And we're going to subtract from it dots plus lines. And so there's 6 dots plus 1 line. So there's 6 minus 7. And so the formal charge for that oxygen is -1. So I can put a -1 here, or if I wanted to, I can just have a single negative sign and that'll be fine. So just remind yourself when you see a single negative sign, first off, this is not a real charge, it's a formal charge, which I said was a fake charge. But remind yourself when you see a single negative sign, this is a formal charge of -1. Okay, so this chlorine looks a little bit different than what we've done before in that it now, instead of having a single bond to the carbon, has a double bond. So we might expect that its formal charge has changed. So what I'm going to do is calculate its formal charge. And so it's going to be its valence 7 minus 4 dots plus 2 lines. So what you can see, it has a formal charge of +1. So I can put +1 here or a plus. Now how about this chlorine? Well, you can see it has exactly the same structure as this chlorine here in resonance form A. And we figured out, we calculated that this chlorine has a formal charge of 0, so this chlorine will have a formal charge of 0 as well. So just to clean things up a little bit, let me get rid of these. Okay, so far so good, and we're doing fine. Okay, and so the final resonance form C, let's just look if we can find, for example, this oxygen atom, if we can find a similar oxygen atom in a different structure. and use that formal charge. And so what you can see, this oxygen atom is a single bond with 3 lone pairs, and so it should have the same formal charge as in structure B, where it was also a single bond with 3 lone pairs. And so this has a negative formal charge. This chlorine here in structure B is double bonded with 2 lone pairs. In structure C, it's the same thing. So this will have a formal charge of +1, and this last chlorine will have a formal charge of 0. So the question is, we have gone ahead and we have figured out the formal charges of all the atoms in each of these resonance structures. What did they tell us about which resonance structure may have a lower potential energy? And the rule is basically this. If all the resonance structures, A, B, and C, had all atoms and they all had formal charges of 0, for example, or they had the same formal charges, then they would be all equivalent resonance structures and they would add equivalently into the resonance hybrid. But that is not the case here. With structure A, we have a structure here where all the atoms in this structure have a formal charge of 0. Structure B and structure C are different. 2 of the atoms have retained a formal charge of 0, but 2 of the atoms have now a new formal charge, one of -1, one of +1. There's some rules that you have to know where you determine based on the number and distribution of formal charges, how does that determine the potential energy of the molecule? And one of the rules you have to learn is if you have 2 resonance structures and one resonance structure all the atoms have no formal charge, but in the other resonance structure, you have formal charges, then the one with no formal charge has lower potential energy. So this is a low potential energy structure, and then these other 2 structures have a higher potential energy. Now let's think about, do B and C, do they have higher potential energy than A? Yes, they do, because they have formal charges. Now, they have a higher potential energy, but is the potential energy between B and C, is it the same between B and C? And the answer is yes, is that both have now the same formal charges, and that they both have, B and C both have 2 atoms with 0 formal charges and 2 atoms with a negative positive. It's just they're on different atoms. And so if that is the case, then they should have a equivalent energy. So now, one of the things I want to digress to by kind of going over here onto this slide here is to point out some of the rules that we have for evaluating formal charge, in which you have to know. So let me kind of point out the first rule here, which is on top. And the rule is Lewis structures with lower potential energy are preferred in a resonance hybrid than ones with higher potential energy. We're going to see that in a minute. Now, the next rule, which we just applied, is this. For neutral molecules, a Lewis structure in which there is no formal charge present has a lower potential energy to one where there are formal charges present. And so in the example we saw, the Lewis structure A had no formal charges, but B and C did have formal charges, and I kind of pointed out A will have a lower potential energy and make a bigger contribution to the resonance hybrid, which I'll show you in a minute. And then there are a couple other rules. I will let you look at those on your own. I'm not going to apply them in this lesson today, but I will probably apply them in class. So let me go back to the glass board and let's just sort of make some conclusions as to what the hybrid structure looks like. So I'm here back at the glass board. So let's take a look at what the resonance hybrid looks like. So here we have carbon in the center, and we have oxygen, and then we have chlorine, and we have chlorine. And so one of the things I want you to see is that we again have a situation where we have, from the carbon, 3 bonds going out to other atoms. And so one of the bonds is a double bond, and the other bonds are single bonds. And so if these structures were equivalent in energy, then what we would say is that, well, it looks like the bonds to going to carbon from oxygen and carbon to chlorine, they would all be 1 1/3 bonds. Again, because you have a double bond mixed in with oftentimes 2 single bonds to give you 1 1/3 bonds. But here's the problem. This has a lower potential energy. And if this is the case, then this resonance form dominates compared to these other two resonance forms, which means what we should say in the resonance hybrid is that the bond between carbon and oxygen will have more double bonded character than, say, the bond between carbon and chlorine. So when we draw a resonance hybrid now, we have to somehow indicate that there's more of a double bond between carbon and oxygen than between carbon and chlorine. So how do we do that? So here what we can do is we can draw dashed lines, say, to carbon and oxygen, and then here with carbon and chlorine, for the other bond to carbon and chlorine, we can draw maybe dotted lines. And so what I'm kind of hoping that you can sort of see is that this bond between carbon and oxygen is different. It has more double bond character as indicated by the dashed lines. Here, carbon and chlorine, it doesn't have as much double bond character as the one to carbon and oxygen. Now, I cannot accurately quantify how much of a bond is between each of these atoms, but let me just throw out sort of an example. So if carbon to oxygen has more double bond character than carbon to chlorine, what I might say is, okay, well, I think instead of having this bond here being 1 1/3 bond, let's make it a little bit of a closer to a double bond now. So we'll say that this bond is 1 2/3 bonds, right? And so here in the end, if that is the case, we're going to have to make these bonds to chlorine have less strength than 1 1/3. And so what this could be, it could be 1 1/6 of a bond, and this could be 1 1/6 of a bond as well. And so this would be a perfectly good resonance hybrid to describe this molecule. So let me just again indicate here again, this is the resonance hybrid. Okay, so let me do one more molecule and then we're done. Okay, so let me do one more really quickly, just another example. Okay, so let's look at the molecule boron trichloride. So we have boron trichloride. And so I'm going to let you figure out how many valence electrons are going to be distributed in this molecule. And what I'm going to do is just write out at least one correct Lewis structure right now really quickly. So we have boron in the center, and we have it bound to 3 chlorines like this. And so you can work it out, but you could go ahead and put lone pairs around the chlorines like this. And this is actually a perfectly good Lewis structure for this molecule, BCl3. Now you might say, well, wait a minute, doesn't that need an octet? And so just to remind you that if you have elements in group 3, they don't need an octet to have a stable atom. You can have 6 electrons and they'll be a stable atom. So this is a perfectly good Lewis structure. So, but as you might sort of suspect right now, you could write some other correct Lewis structures. And so let me just give you an example of another one you can write. So for example, what we can do is we can move this lone pair into the bond between boron and chlorine. And so what will that look like? It'll look like this. And so we have a double bond to this boron. And so we have this, the other chlorines are fine. So they look like this. So this is a correct Lewis structure. So now boron has an octet, which is permitted, and then the chlorines, all of them have octets, which is permitted. So you can probably imagine that we can write a couple more. So let me quickly write out the 2 other structures that you could have. And so here all we're doing is just moving the location of the double bond, and it's going to another atom like this. Another chlorine atom. So this is another good Lewis structure. It is correct. And so this here is the final one. We're having the double bond going to the lower chlorine. So this should be a correct Lewis structure as well. Okay. Now, of these 4 Lewis structures I have written, we'll call this one A, this one B, this one C, this one D. Are these structures equivalent in energy or does one have lower potential energy than the rest? And so I'm hoping you know the way you evaluate that is you would have to figure out what the formal charge is for all the atoms in the structure. And I think I'm just going to go ahead and quickly give you the example for that. But let me just do one. Let me just do one really quick. So let's say you have boron here. Can you calculate the formal charge for boron? So it's going to be valence of 3 minus 0 lone pairs. So there's 0 here. And then there are 3 lines. And so here it is 0. So the formal charge for this boron is 0. And like we've seen before, these chlorines also have 0 formal charges. So this Lewis structure here has formal charges of 0 on all the atoms. Okay, let's look at this next one. So boron has a valence of 3. There are no lone pairs, but there are 4 lines. And so this one here, boron should have a formal charge of -1. And now we have here chlorine here. As we saw before, this has a formal charge of +1. This is 0, this is 0. And the other two are similar here. And so here, this is going to be a formal charge of +1. This is a formal charge of -1, 0, 0. And so I'll just complete this one here as well. Okay, now can you figure out which Lewis structure is going to dominate the resonance hybrid? And what you can clearly see, it's going to be the Lewis structure which has no formal charges. And so it's going to be this one here, where boron doesn't have an octet. So how do we draw a resonance hybrid of all these 4 Lewis structures? Well, what we would try to indicate is that, well, we do have a double bond kind of going off to 1 chlorine out of 3. So we might expect that there will be some double bond character between the boron and the chlorine. It's just not going to be 1 1/3 bonds. It's going to be a lot less than that, because here the structure that dominates does not have a double bond between boron and chlorine. So the way we would write this as a hybrid structure, I'm going to write it over here, is we would have chlorines here and sort of indicate that they have a little bit more than single bond character, but it's not even close to double bond character. You might put in little dotted lines here. And so, for example, maybe these bonds to the chlorines, they're not going to be 1 1/3 bonds here, right? Because here this structure dominates and it has no double bonds. So this is going to be like 1 1/10 bonds or 1 1/20 bonds. So we'll just say, for example, this is like 1 1/10 bonds. Okay. Now there's one more thing I kind of want to mention. And then this is the last thing I'm going to say. So remember when we were drawing in the last lesson structures, Lewis structures of ozone? So let me quickly draw those out. So we had ozone here. Looks like here's one Lewis structure for ozone. I'm not going to draw the other one. But when I drew out these structures, one thing I sort of neglected to do was to include formal charges on the atoms. And typically when you write Lewis structures, most chemists like to include formal charges on the atoms. So just to point out, this was a correct resonance structure, but if you're a really rigorous chemist, then you add formal charges onto the atoms, and you can calculate them on your own. But basically this oxygen would have a negative formal charge, and then this oxygen here will have a positive formal charge. Same thing with carbonate. So carbonate looked like this. So I'm drawing one Lewis structure, which was correct. Okay. And so you can work out the formal charges, and then this oxygen has a negative formal charge, -1, and this oxygen has a negative formal charge. And actually, one of the reasons why I want to draw formal charges for these molecules is to point out an important fact that you need to know about formal charges, is that when you add up the formal charges, they should be equivalent to 0 if the molecule is neutral, or equivalent to the charge of the molecule if it's an anion or a cation. So with ozone, O3 is a neutral molecule. It doesn't have a positive or negative charge. It's just O3, right? And so what we hope is if we write in formal charges into the structure that they would add up to 0, and they do. You have 1 plus, 1 minus, and that's 0. So that's consistent with the idea that ozone is a neutral molecule. Now how about carbonate ions? So it's CO3 and it has a net charge of -2. And so again, your goal is if you do have to put in formal charges with atoms that they need to add up to the net charge of the molecule. So here we have two negative charges, two formal charges, and they add up and they are equivalent to the net charge of the molecule, which is carbonate. Okay, and so one final thing again is just to point out, when I was evaluating Lewis structures to figure out which one had the lowest potential energy, the way I was doing it was I was looking for the Lewis structure that had no formal charges and said that would be lower potential energy than the others that did have formal charges. But there are a couple other additional rules here which you can see on the screen. There, I'm pointing in the right direction now. And so I would encourage you to look at those and we'll do some practice of those hopefully in class. So thank you for listening and we will see you next time.